Good morning, everyone. My name is Sainath. So my name is pronounced similar to the Greek symbol psi with a subscript 0, so it's Sainath. So yeah, I'm a PhD student with Dr. Rajibul Islam's group, and today I'm going to talk about the advances our group has made towards the quest of building a trapped ion quantum simulator. So this is going to be like an experimental work. Uh, so this is going to be the outline of my talk. It's more like a teaser to grab your attention. My talk consists of three parts that are slightly in the the disconnected directions that our group is working to solve the problems of a common goal of building a large-scale trapped ion quantum simulator. So I'll start by introducing you to the platform of the trapped ion quantum simulator. Here, I will be explaining the nature of the qubits and how they interact with each other. Uh, Followed by that, I'll be talking about the holographic beam shaping. This is to solve the problem of individual ion addressing. That is one of the major problems in realizing a large-scale trapped ion quantum simulator. So here I'll also be talking about how we use a single atom as a sensor to calibrate and compensate for various optical aberrations introduced by the optical elements. So the scheme we have here is implemented in our existing ion trap called Fourier trap. So in the next segment, I'll be taking a jump and I'll be talking about the another ion trap that we are building. It's called blade trap. So this aims to perform large-scale quantum simulations with around 50 to 60 ions under pristine trapping conditions. And in the end, I'll end the talk by introducing to two different parallel efforts that are under progress in our group. So one is the theoretical investigation of the possibility of trapping 2D chain of ions in optical trap. And another effort is quantum ion. So this is the open access trapped ion system that is going to be completely automated so that theorists can perform their quantum algorithms in it. So I hope I have excited you enough by showing pretty pictures. So let's jump into the talk by asking the first question. So what is a quantum simulator? So a quantum simulator is a highly controllable test bed that can be used to mimic the interactions of an uncontrollable quantum state. So this involves state preparation, evolution, and simulated unitary, and then measurement. So such a simulator can be used to study dynamics and properties of the target system. Realizing a quantum simulator has various uses, starting from providing insights in condensed matter physics, high energy physics, and to applications like drug discovery and quantum chemistry. So a quantum simulator is pretty useful. So let's jump into like how trapped ions can be used as a quantum simulator. So this picture here shows a typical configuration of a linear chain of an ion trap. So due to properties such as long coherence times, close to 1 hour single qubit coherence time that was realized pretty recently, and ease of state preparation and isolation, and ability to induce long-range fully connected spin interactions make this system an ideal candidate for quantum simulation. So due to long-range interaction, this system is equivalent to a fully connected graph. So this means that you can perform entangling operations between any arbitrary pair of ions, not just nearest neighbor, in contrast to, let's say, other cold atom realizations. So our quantum simulator consists of a linear chain of 171 ytterbium ions in a Paul trap. So here the ground state hyperfine levels of each qubit act as a spin half particle. And these spins are separated by a distance of 3 to 4 micron. And interaction between them can be mediated by collective motional modes of the ion chain that the ion exists in. So chain of ions trapped in a harmonic confinement. So if you have a chain of 9 ions in a harmonic trap or close to a harmonic trap, you have a set of collective normal eigenmodes in transverse and longitudinal directions. So the picture here shows the set of transfer eigenmodes for a chain of 9 ions. So the mode of highest frequency is called center of mass mode, where all the ions vibrate in phase, and the next highest frequency mode is called the tilt mode, and then followed by the other modes. So these modes are used to mediate the spin interactions, which we'll be seeing in the following slides. So to understand how the spin interactions between these ions are mediated, consider a case of 2 ions trapped trapped. So here, each ion is described by its spin and a motional quantum number. So by introducing a pair of global beams with frequencies nu1 and nu2, such that the difference between the frequencies is nu beat naught, we can induce a spin flip as well as add an additional quantum. So this pair of lasers effectively drive this transition between the spin up and spin down. Excuse me. So now by introducing another pair of lasers with a frequency difference of nu prime beat naught, now you have a jungle of levels. Now you can couple the down state of this two spins to the up states of resonantly. So this pair of lasers create an effective sigma x Hamiltonian, where the interaction strength Gij depend upon various experimental parameters such as laser intensity and the detuning mu. So these are the two important parameters. The capital omega and the mu are the important parameters when playing with the Gij. So now by changing the detuning mu in the previous expression that I have showed, across the mode frequency of ion chain, one can achieve various interaction profiles. So just let me start laser pointer. Yeah. So by choosing mu close to the center of mass mode, we can achieve an interaction profile where the interaction strength is independent of the ion index. And by choosing the mu close to the tilt mode, we can explore an interaction profile where the interaction strength increases by distance rather than decreasing. So we can explore various such kind of interaction profiles, but these are only limited. Because of the single parameter mu. So the question now is, can we simulate arbitrary interaction profiles? So such an ability would allow us to simulate systems such as spins on a square lattice or a Kagome lattice. So this can be achieved by a multi-frequency extension of the scheme that I have presented like in the previous slide. So the difference between the previous scheme and the current scheme is that now instead of global beams where the laser beams were shining on all lines, now we need local control. So you need local control of intensity and frequency at the level of single atom. So the key ingredient to achieve an arbitrary interaction profile is the single ion addressability. So this requires precise optical engineering which becomes the motivation of the next segment of my talk. So the next segment of my talk talks about holographic beam shaping, which gives us the individual ion addressability. So yeah, let's jump into this segment. So before introducing to the details of the optical scheme, let me introduce to our test bed ion trap called Fourier trap. So on the top, you have a CAD design showing various components such as vacuum pumps, vacuum gauges, and other electrical connections. So on the bottom picture, we have a picture of the actual setup, which shows the vacuum chamber and magnetic field coils and the resonator. So at the heart of this vacuum chamber is the ion trap, which is made of 4 rods and 2 needles on which we apply static and oscillating electric fields to trap a linear chain of ions. So this is a quick primer on our experimental setup. So now let's see how we achieve single ion addressing. Yeah. So we achieve single ion addressing using something called Fourier holography. So this is achieved by a device called a digital micromirror device. So digital micromirror device, as shown in this picture, is an array of millions of tiny mirrors, which are of about 10 micron size and can be flipped at the rate of tens of kilohertz. So in our setup, so the light coming from this optical fiber FC is expanded using the lens combination of L1 and then modulated by the amplitude halogram that is written onto the DMD. So the light, so the lens L2 collects the light from DMD and then focuses onto the image plane IP1. This lens effectively performs a Fourier transform of this hologram onto the DMD. So the light from IP1 is then relayed onto the ions here using the lens L3 and the objective, which this also additionally adds a magnification. So the fluorescence of ions is collected using the same objective OBJ using onto the camera C2. So we can have elaborated profiles to generate a given pattern to the image plane. For instance, if you note this figure shown here, where the yellow pixels represent the on state of mirror, and so this would generate a profile as shown here of 5 Gaussian beams. So each yellow dot here is a Gaussian beam on the image plane. So the imperfections are because imperfections in this image is because of the binary nature of the DMD. Like the mirrors can only be on and off. So one of the challenges in implementing such a nice scheme is that there are so many optical aberrations that are introduced by various lenses, objective, and even the DMD. So to mitigate this issue, we use the single ion in our trap as a sensor to measure and compensate for various optical aberrations. So let us understand how we perform the compensation of these aberrations. So let us say we start with a single yellow patch as shown in this figure on the Fourier plane. So this will be returned to the DMD. This produces a corresponding area disk pattern on the image plane of ions. So if we introduce another patch, the light falling on these two patches interfere on the image plane and produces interference pattern. And notice that there is a bright fringe in the center. Now, if there is an aberration between these two patches, it can be modeled as a phase difference between these two patches. So in this case, if the phase difference between these two light falling on these two patches is about pi, you see a shift in the interference pattern on the image plane. So now you see that there is a dark fringe on the spot of bright fringe. So now we can use this to characterize our aberrations. So how do we do that? So we measure the phase shift generated by the aberrations by varying the phase of one of the patches with respect to other, and fit it to find the phase difference. And now you apply that obtained phase difference delta phi onto the Fourier plane, and then you can cancel the aberrations. So in our setup, we use ions as the single sensors, ions as sensors for measuring the aberrations. So similar to the scheme as shown in the picture in previous slide, we use DMD to create these two patches, and which selectively allow the light to interfere with respect to the central patch. So since we only have amplitude control on the DMD, we don't have any phase control. We need to create a grating inside each patch. So you can see the blue lines here. It's a grating inside each patch. So this leads to interference fringes on the ion plane here. And since the fluorescence of ion is proportional to the intensity, we can see a sinusoidal variation. So when we vary the phase of phi I, we can see a sinusoidal variation of photon counts. And here, different colors, like curves in different colors, represent the similar experiment for different patches. So we use these measurements to extract the phase map of aberrations. So here is a phase map extracted from the previous measurement across the Fourier plane. So we use this phase map to compensate the optical aberrations and achieve the diffraction limited addressing. So to verify this claim, we scanned a laser beam across the ion before and after aberration correction. So the blue curve here represents the beam profile before the aberration correction, and orange represents the one after. So you can see that most of the energy, most of the power lies within the area disk radius, single area disk radius. We can confirm that we have achieved a diffraction limited addressing using our scheme of aberration correction. So now that we have achieved single ion addressing, we need to characterize it. So one of the important metrics for single ion addressing is the crosstalk. So neighboring ions should not be disturbed while addressing any particular ion. So to characterize this, we again use the single ion to measure weak light. So how do we do that? So the plan is to characterize the quality of the generated beam with high sensitivity. So a good beam should be contained only in the region of a single ion. So to achieve this, we trap a single 171 ytterbium ion, which has this energy level, energy levels as we discussed before, where the downstate and upstate are separated by a frequency of 12.6 gigahertz. So we initialize the qubit to a downstate using optical pumping, and then send cooling or depumping light through the DMD. So what this does is, if the DMD light hits the ion, then it will bring the spin state to upstate. If it misses the ion, then the ion will stay in the downstate. So so this can be used to see if the light is actually any small light is hitting the ion or not. So alternatively, we can also perform Rabi flops by additional microwave driving this transition between the downstate and upstate. So this will enhance. So when the DMD beam is present, the ions will like there will be enhancement in the ion decoherence, and the coherence time, from the coherence times we can extract intensity of light on the ion. Additionally, we can also perform Ramsey interferometry such that the DMD is active during the wait times. So hence showing a decrease in the coherence time as well. So let me show the a few preliminary results of this these measurements. So this slide shows like this part shows the measurement for the Rabi flops. So on the left, you can see the timing diagram. So we start by setting the dx, that is the distance between the ion and the spot where the DMD light is being focused. So it's called dx. Then we pump the ion to the downstate, followed by microwave that is driving the transition between spin up and spin down, and the DMD light, and then we do a measurement, state detection. So the graph on the right shows the time versus the average photon counts that we obtain. So a photon counts are like zero, almost zero photon counts means that the ion is in the downstate, and then high photon counts mean that the ion is in the upstate. So we see that there is a reduction in coherence time versus the shift of the DMD beam in the image plane as expected. So the green curve shows the Rabi flops without the influence of the DMD beam, and as we move the beam closer to the ion, we see that the coherence time becomes shorter. So you can see that the orange curve is features a smaller coherence time than the blue curve, because the beam was closer to the ion. An analogous effect can also be seen in the Ramsey oscillation decay, where the DMD beam reduces the visibility of these oscillations. So similar to the previous experiment, we have the timing sequence here, so where you set dx, pump the ion to the downstate, followed by pi/2 pulse, pi/2 pulse of the microwave, and then you turn off the microwave and have just the DMD light focused at a distance dx, and after the wait time, you have another pi/2 pulse. So the graph here shows the delay time versus average counts again, and we can see that the blue curve is the one without the DMD beam, and the red curve is with the DMD beam at a distance of 5 micron. So from these measurements, we can extract the beam quality, and further measurements are being performed to benchmark our single ion addressing using this technique. So we are still performing more measurements to characterize this better. So another cool application of using ion as a weak light sensor is that we can use it to measure arbitrary beam profiles in the ion image plane. So on the left, you can see that this animation shows a series of 2D images performed by shifting the beam in x and y direction. So similar to dx, there's a dy where you shift the DMD beam across the perpendicular direction. So each pixel represents a single experiment for a given dx and dy, and then you change dx and dy to get like a single picture. So in this picture, we changed the defocus term, and which effectively translated the focal point of the beam across the in the ion plane. So you can see that the extreme sensitivity of the measurement, that with only little light, we can see the defocus rings using this measurement. So we are not just limited by Gaussian beam profiles, like single. Like we could also measure Legor Gaussian or donut mode produced by produced by measurement from the ion by similar 2D scans. That's pretty cool. So with that, I conclude the holographic beam shaping part of my talk and take a jump to the next segment of building a large-scale quantum simulator. It's called a blade trap system. So this slide lists the broad goals that we have in building the new ion trap simulator. So it's the ability to trap large number of ions that can be individually controlled and programmed arbitrarily, and to program arbitrary interaction graphs. Also to perform high fidelity direction of spins. So with those goals in mind, we start our design, and the picture here shows the CAD design of the blade trap system. So design goal is to trap around 50 ions with control over spacing between the ions that is required for high fidelity addressing. And then we need high optical axis around 0.5 Na so that we can get high fidelity detection. And then we want to reduce decoherence from any background collisions. So for that, we need to create the chamber in extreme high vacuum, where the pressure is expected to be smaller than 1e-12 millibar in the region of ions. So the trap is made of 4 blade electrodes for us to allow high optical axis, and this is made of thin wafer blade electrodes, where each electrode is itself segmented into 5 electrodes for us to give a better control over potential. So let us have a closer look at the main chamber. So so at the heart of the chamber lies the blade holder that holds the blade. So one of the requirements of choosing the material of this holder is that we should have better thermal conductivity while having good electrical isolations. So while applying around 1 kilovolt of static oscillating and static voltages, this could potentially generate heat, and we want to minimize and characterize the heat generated. So we have an additional feed through that enables the temperature measurement of the trap and other structures. We have these 3 yellow feed throughs that power our atomic sources, and then the system is built to have high optical axis in all 4 directions. So that and then we have 4 recessed viewports so that we can collect light, so that we can place objectives as close to the ions as possible. And the side reentrants give an NA of 0.5, and the top ones give an NA of 0.3 for probing and state preparation. So another requirement while building this system is the low decoherence from background collisions, as I talked before. So using MolFlow and open source Monte Carlo software, we find the steady state pressure of the we simulated the steady state pressure, and we estimate around 5e minus 13 millibar at the region of ions, which is let's say 2 orders of magnitude better than the current state of room temperature ion traps. So currently we are progressing in doing vacuum pre-bake of this system. So this picture here shows the progress of a vacuum pre-bake, so that this process is done to remove the dissolved hydrogen from the stainless steel components, which becomes one of the major gas loads. So what we do is we heat each stainless steel component at 400 degrees for around a month, and then introduce air to create a chromium oxide layer to further create a diffusion barrier. So this recipe would potentially give us 1e minus 15 millibar liters per second centimeter square outgas. So before concluding on the blade trap part, I would like to quickly highlight other effort that we are doing for the blade trap is to produce the compact optical setup. So the idea is to miniaturize the optical circuit by using a CNC machined block instead of using instead of traditional approach where you use pedestals and forks. This would improve stability and also ease of building such optics. So with this, I conclude the part on the blade trap system. And before ending my talk, I would like to quickly give a teaser on the other two projects that are being going on in our group. So one is the theoretical investigation of trapping 2D chain of ions in an optical trap. So the idea is similar to traditional trap, but the axial confinement is provided by the tightly focused light inside a cavity, and the radial confinement is provided by the DC electrode. So the picture here shows a simulation of a numerical simulation of 13 such ions, equilibrium position of 13 such ions inside this such trap. So
Sainath, you
just 2 minutes.
Yeah, we're getting towards the end. Okay, so you wrap it up.
Yeah, yeah, almost done. So the motivation of this is that with 2D traps we can trap large number of ions in a small space similar to 1D chain, and also optical trapping mitigates the major problem of micromotion that we usually see in the traditional radio frequency traps. So these are some of the numerical results that we have here. So the plan is to use around 130 milliwatt of 1064 nanometers, which minimize the off-resonance scattering. And the plots here show equilibrium positions of one such configuration with tens of ions. So we are currently working on estimating the fidelities in such trapping conditions, and we'll see if this trap can be used in a large-scale trap-down quantum zero. So currently we are just numerically estimating the trap parameters. So another thing before I end is the quantum ion that I would like to introduce. It's the open access trap-down system that our group is building in collaboration with Dr. Senko's group at IQC. So the idea is to build a trap-down system that is operational 24/7 with every aspect automated. So this gives theorists complete control to execute their quantum algorithms with trap-downs. So with this, I would like to summarize that by saying that we have implemented diffraction limited single line addressing using Fourier holography. We are working towards building a trap-down platform for large-scale trap-down quantum simulations, and we are theoretically investigating the possibility of trapping the ions optically. So I would like to acknowledge my group, especially my PI Rajibul, postdocs, grad students, and undergrads, and also the funding agencies. Thank you.
Thank you very much.
Yeah, sorry for rushing in the end.
Yeah, no worries. So are there any questions out there? I mean, one that comes to mind is, so it's relatively easy to do the all-to-all, let's say, easy for me to say. But so how limited are you to sort of, if you really wanted to get just nearest neighbor, can you do it?
Yeah, so I mean, if you have individual ion addressing, which we are like working on, you can do arbitrary individual addressing or what, like nearest neighbor or next nearest neighbor. It can be anything. You can produce anything. I mean, that's the ultimate goal. Just nearest neighbor is boring anyway. Yeah.
Indeed, but okay, but you're not quite there yet. I mean, what?
Yeah. So so that's what we characterized in our test bed. So we are building a large-scale quantum simulator, right? So in that we hope to achieve this single ion addressability with both amplitude and frequency control. So we are not there yet, but we hope to. We solved some of the major problems in our testbed system that we hope to achieve it soon. To a certain extent, it won't be completely arbitrary, but we'll definitely have more control than just all-to-all or just nearest neighbor. It will be limited to few classes of problems.
Right. Thank you. Are there any other questions?
Okay, I'll ask a technical thing, which is you have this new vacuum system, and you say it's orders of magnitude better than room temperature, other room temperature ion traps. Yeah. What did you do that's so different from how other traps are? Your pumps are standard. What's different?
So first thing, as you said, like we are doing like this long prebex pre-bake setup where we heat these stainless steel components for like a month to reduce the dissolved hydrogen. So we expect like 2 orders of magnitude smaller there, just a background hydrogen load. And then basically we increase the conductance. So I think people did not let's say estimate, like did not work on this so hard that like to optimize the conductance from the pumps. So we kind of have huge conductance and big pumps, and we are not using any materials inside that have lower out so higher outlet. So it's basically choice of pumps, good conductivity of like components, and then choosing of materials such that we hope to achieve best pressures. And also this a new recipe of pre-baking would reduce the hydrogen gas load. So it's more or less like choosing of various things carefully so that we want like very good pressure. So because the problem is that, so in our current system we have around like say close to lower minus 12 millibar pressure in our Fourier trap, and we see that background collisions. We see a background collisions in a chain of 10 ions in approximately like every 10 minutes. We don't want that like background collision from background gas. So if we are choosing a 60 ion chain, that will probability will be even increased. So that's why like focusing on this is very important.
Thank you.
Okay, so we're now in the so what I propose to do.
Oh wait, there's one student question. Come on.
Oh yes.
Yeah, if we have another minute. Thanks
Sure.
so much for your talk. That was a really interesting talk. I loved seeing the different projects you're working on. I was wondering, for the holographic imaging, how did you measure the distance of the DMD beam to the ions, or were those estimates? Because you said you were taking measurements at 2.5 microns distance, 2 microns distance. How did you?
So it's more like an estimate. Yeah. So what we can trap a chain of ions, right? Yeah. Now you can scan the beam and see that when it's hitting the first ion, second ion, third ion, and we know approximately what is the spacing of ions. That's one estimate. So there are other like there are various estimates. So yeah, it's an estimate.
Okay, thanks.
I think Daniel has a question.
Yeah, just to be sort of get discussions going and things. Why are you stopping at 60 ions?
There is no point of stop. Like there is no reason to stop 60 ions. You can go for like hundreds of ions. So it's like just 60 ions is like already big enough for us to already hit like so many experimental challenges. So if you're aiming for let's say 500 ions, then you are aiming for so big like so many problems. So 60 ion is like already big enough that like other ion traps like almost cannot do 60 like good high like completely fully connected ions. So it's just an experimental goal that we have set because it's already challenging. It's like as you go even higher, your trap becomes more shallow. That means the voltages you apply on the perpendicular directions have to be increased. Like already we are in like 1 kilovolt. The voltages have to be increased.
Why do they have to be increased? I mean, you worried about zigzag, but is that a complete killer? I mean, if you're doing universal quantum computing, I agree, but for simulations?
Yeah, I mean, even here, like we are, so you don't want it to be zigzag configuration, or
yeah, why not? That's the
because one thing is there are multiple. So when you're aiming for single ion addressing, so we are aiming for single ion addressing, right? So zigzag can have multiple. Let's say it can jump between zigzag states, zigzag and zagzag. You don't want that.
Yeah, so sure. There's
you don't like you don't want that. Like already we don't want the ions to move, and then if there are multiple like multiple states that it's jumping in, your individual beams are somewhere else now. I mean, you can always mitigate that, and yeah, basically like experimental challenges we don't want.
It strikes me as it might be fun to play around with it, just to see what the problems are and whether this can't be put, the envelope can't be pushed a bit.
Yeah, so that's why we are exploring the optical trapping, right? Like
Yeah, of
you
course.
push
Yeah.
even further that it's a 2D crystal now.
Yeah.
And
But
so
what-
the,
how can you do individual dressing when you got a 2D crystal?
you can, because so now the chain is perpendicular to the optical axis. So you can still do, because without like that's a bigger goal. Here we cannot do yet, but that's you can still do, like not using multi-channel AOM or something, but using the holographic beam shaping, you can think of doing it.
Mhm.
Yeah.
I may I'll stop the recording now, okay, for this
Yeah.
session, and then we can just move into free discussion. 1 second.